Boing. Boing. Hola. Hola, povo. ¿Qué tal? That's all I know. Welcome, everybody, back to the Swift and the SwiftUI Learnalong. I am your host, me. And this is episode 35. Should we do an intro today, Jared? We should, yeah. Okay, let's try to keep it brief. Listen, brother, for the uninitiated, this is a stream. I call it, okay, the style's a little different. I'm not here to entertain you. I'm not here to talk to you. It's called the Learnalong for a reason, brother. You see, it's, I'm coining this new term. It's called FOTW. Fly on the wall learning. You see? No direct interaction. But in all seriousness, this is me learning Swift for the first time. And I will be, let's say, narrating the book Swift Programming, The Big Nerd Ranch Guide, 7th edition. So I narrate this book out into the ether for anybody watching, and for anybody watching the may catch the future edited videos of the stream. But the whole idea is that you're literally watching me learn, and I narrate it out loud. I talk out the concepts out loud, but it really is me learning. So that's really the distinction here that I want to make known to anybody that wants to watch, because as somebody that I'll say recently got into the programming biz, just a few years now, I'm still fairly new to it, and Swift is my first proper deep dive. So this isn't like some influencer type thing where I've arranged a bunch of examples and I'm trying to make it seem more appealing, or trying to, I don't know how else to explain it, but I think you know what I mean. This is legitimate learning, and that's just what it is. I don't know. It's very crude, very raw. Okay, let's say that. Just so you know what to expect. Now, aside from that, there's really nothing else to apologize about, because there's no other way to do it. And so if you feel like you gained something from this, then please do follow along. Happy to have you. But if not, just know that, I mean, this is effectively what we do here, right? So we're gonna learn Swift, or we have been learning quite a bit of Swift, matter of fact. So like I said, this is episode 35. Every bit of the Swift learning that I've done has been on this stream. So if you wanted to catch up, all of the streams are, they've been recorded. They're just sitting there on X or YouTube, wherever you're seeing this at. And eventually they will make their way to a YouTube playlist and an X playlist, where these streams will be chopped down and edited so that all this extra fluff can get pulled out, at least as best I can. Or Jared will do it for me, maybe. He's saying no, but okay. So, but after we get through this book, we're making some good headway here lately. So page 564 of 818, we're getting there, baby. We're gonna dive right into SwiftUI after this book. So I'll use a different course that I purchased for that I will share with you guys. Fair use, by the way. But it'll be much of the same fashion, but it won't be a Big Nerd Ranch Guide book. Okay, so that'll take us, or that'll complete SwiftUI. After that, I want to do a little bit of just to take a break from the endless syntax and rules and all that stuff. We'll take a break and do some schema design for my application. So this stream is not just about learning Swift. I want to learn it for a specific reason. I started a company, a startup, if you will, and there's a product in mind. So I'm going to design all of that, out in the open. We're going to do it all here. And I won't get too deep into what it's going to do, but it's going to be called MRP Panda. If you know what material resource planning is, if you've ever worked in or around ERP systems like SAP, Microsoft Dynamics, things like that, effectively you probably, to some degree, you can understand what MRP Panda is going to do, but it's going to help people, make purchasing decisions based off of, sales demand, how much you got in stock, how much you got on the way, how much raw material do you need, when do you need it by, what's the transit time to your customer, all of those different elements that businesses have to, anybody that manages physical inventory, anybody that makes stuff and then has to get it somewhere by X is effectively my demographic. So that's what it's going to do. And so I spent 10 years in that space. I did a lot of implementations, going on site, interacting with mostly food distributors. So a lot of interesting problems around traceability that FSMA introduced, but we'll get on into all that later. Just know that there is a legitimate company being built right before your eyes, and I love this whole. I just have a lot of love. No, I'm kidding. No, but this has been a great experience. I think Swift was a great choice. The more and more I learn about it, I think anyone that's been following along probably has that same kind of feeling, I would hope. Just because it's been very impressive, for the most part, very, very impressive. Some stuff that I don't like, but honestly, I come from, I wrote a butt ton of SQL. I know SQL very well. And then a little bit of Golang. I wrote some ETL pipelines in Golang, but Go just felt a little more, hammer and nail, whereas Swift seems like a power toolkit, if that makes sense. But yeah, that's the concept behind this stream. Okay, so raw learning. There's a ton of content coming, and we're not here to talk to each other. Okay, we're here to learn. And those are the main tenets of this stream. Aside from that, I hope you enjoy, and now we can get it popping. All right, so yesterday, I think I'm leaning into this format here. I like doing the recap, so just to kind of get the lay of the land in terms of where we were. Main things that were covered, I'll say. Oh, one other thing. That's not important. Not really important. Let's see. Okay, yesterday we learned, let me look through the code here. Protocol exercise. This is something we've seen before. So in this case, right? Well, now this isn't really new, but this is just saying that the protocol exercise itself must also adhere to this other protocol, custom string convertible. But yeah, and that's not really interesting. We learned that like 2-3 episodes ago, so this isn't anything new. Oh, the self. Okay, this was the hot topic for me yesterday because I was really having a hard time. It's still not completely there, but it feels way better. And I did take a lot of notes and put it on our public board here, where I'm keeping all of the really impactful isms, I'll say, just little nuggets that I've talked through on the stream just to kind of understand better what the book is teaching. There's the one on self right there. I may need to come back and reference it, but we'll see. But anyway, this is where I'm going to keep these kinds of items. There's a lot more that I need to pull out of the book, so I'm either highlighting in the book itself. I really just got to get everything out of Kindle. Like, I don't know why they made this. I don't know how apps, the longer they're out, get shittier. I'm not sure how that works, but yeah, Kindle has gotten shittier, and I do regret. Again, I'm getting off track. I don't want to be negative. Okay, so anyway, let's talk about self. Let's talk about self. Like, meaning not myself, but capital S, self, which matters. So capital S, self, is used just like the dot self that we've seen elsewhere, except capital S self is a type that is isolated to use within protocols and protocol extensions. And it's just a way to refer, just like the dot self, except a little bit different. But effectively, let's see, where do we use? Okay, here's a good example. So when we're using protocol extensions, right? If, like in this case, we're extending the protocol exercise, which was up at the top there, and we're adding this method. So effectively, this would be like, by extending the protocol exercise, any type out there, like in this case, elliptical workout, right? This is a type and it conforms to exercise. So by extending exercise here, we are adding this method to any type that already conforms to exercise. And if you recall, when we extend protocols, one of the things that you have to remember is, while it's very convenient and you are able to effectively add functionality to every type that already conforms to protocol without even modifying the protocol itself, meaning directly, because here's the protocol itself, right? When you do that, it does not translate the enforcement portion. And probably easier if I just visual select. Oh yeah. And then how do I cut this out? Did I just do it? P. Cool. Wow. You know, Vim is pretty cool. Some of it anyway. I actually think, it's not really a hot take here, but I think Vim motions are, like, you probably can't see them, but Xcode has a Vim mode, and it shows you at the very bottom, down here. I don't know if y'all can see that, but it shows you the shortcuts, like not all of them, of course, but the more applicable ones. And it's been a great way to learn Vim. I mean, if whatever. I'm just saying, I like Vim motions inside of other editors. I think it's great. For a while, I was using Helix, which is basically Vim with some differences, different paradigm shift between verb action, but it doesn't matter. Very similar. But I used to use that inside of VS Code, just so I could have some of the tools. Like, I like some of the interface things in VS Code, but in the window itself to edit code, I would just use a terminal window and use Helix inside, which was cool. But I like this too. Like, having the shortcuts there is a massive help. Anyway, that being said, now let me put this here so we can, is it P? No, P. Yeah, cool. Okay, so look at this here now that we have it side by side. So whenever we extend this protocol exercise, anything that's in the interface itself, directly in the protocol's body, all of this gets enforced, meaning anything that adheres to, let me get this up here too, that'll probably be a good idea. GG for the top of the file. Oh yeah. And then P. Yeah, okay. So this type, elliptical workout, conforms to exercise. Now it has these two properties, right? These are the protocol's direct conformance requirements, meaning anything that conforms to it, in order to conform to it, meaning in order to even let it build, in order for the compiler not to give you an error, you got to have these properties with these names, with these types, and they got to match these properties being get and set. So get just means it needs to be a readable value, set means it needs to be writable. Okay, so this is the minimum that something needs to conform. And wait, but here we have elliptical workout conforming to exercise. But we only have two. Oh, okay, I remember that. Yeah, we only have two of these, right? So we have calories burned and minutes, which are these two. But we don't have title. And yet we don't get an error. Why is that? Well, this extension here is extending exercise. And what we learned is that in the protocol itself, right? So title. You can't do this directly in a protocol. This being a computed property. So this is saying that for the title property, it's going to be a string, and this is the string representation that it should return if you call it. But you can't put computed properties, which is this little closure here. You can't do this up here, just to demonstrate. So that gives me an error. So you can't do that, right? It's only, pardon me, it's only the signature aspect of it that we want here within protocol interfaces directly. But since we're extending exercise, this still gets associated with the protocol. Therefore, by conforming to it here, it actually does still inherit this default implementation. Now, the other thing that we learned in that same sense was that there was a weird kind of behavioral thing to observe, and let me find the example where they showed us that. Yeah, here. Okay, so you see this constant, this let 10K run. It's of type running workout, which running workout is up here. It's just another struct that conforms to exercise, okay? And we have this property, let title. So it's a constant named title, contains a string, gotta go fast, right? So if we go back to 10K run, oh, where'd you go? Here. So when we initialize 10K run, type running workout, we're setting it equal to an instance of running workout. Instance meaning a unique object, but it has these properties from running workout. And it has these values for each of the properties. So for calories burned, this 10K run instance would have 750 in the calories burned bucket, 60 minutes, 10,000 meters, so on and so forth. Okay, so that gets initialized, right? Immediately after, we initialize another constant. This one conforms to the exercise protocol directly, which matters as we have come to find out. But we're setting the value equal to 10K run, which is what we just created. So initially, since they run one after the other, they would have the same content, separate instances, 10K run and workout, but the same value, same properties, everything. Except what we learned is there's two different ways you can go about, I guess you could call it controlling the hierarchy or how the protocol inheritance works. Okay, so the first way that they showed us, it was just like this, just this example here. But when we ran it, let me go ahead and run this, wake it up. Okay. So you can see, so here's our object, right? Those are the values we got. Yep, cool. Title, gotta go fast. And then for workout, let me get out the way. And then for workout, we get the same values, right? 750, 60, 10,000, gotta go fast. These values only match because we have, so we looked at the extension, right? Where did it go? Where's the title? Oh, here it is. So you see this extension, right? Exercise. So this is what they refer to as a default implementation. So anything that conforms can use this default implementation of title. But the only reason that those two values match is because we also have title listed in the protocol interface itself. Well, what does that mean? Well, I'll show you, brother. So we get rid of this from the protocol interface, right? And so now we only have the protocol itself with these two properties that are required directly in the protocol body: calories burned and minutes. And we're only left with this default implementation of title via an extension. Okay, so when we first ran it, both, I guess you can see it easier here, but when we print 10K run, which was this instance of type running workout, when we print that title, it's got to go fast. When we print the other instance that we copied from 10K run, conforming directly to exercise, we get the same thing, got to go fast. That was before. Now we've removed title from the protocol interface directly, right? So that's the difference. So if we rerun it, now we get different result. So got to go fast for 10K run, but for workout, so this instance here conforming directly to exercise and not running workout, we get a different title. We get the default implementation instead. What they conveyed to us was that you can do it one way or the other. So they're more or less trying to just tell us to be aware of that behavior. Not that necessarily there's a right or wrong way to do it. So it's just a thing to know, right? So if you wanted to, well, how about this? I'll just say this. For my preference, just to keep it simple, I like not having the var title here and just leaving it as an extension, because this means that now the type that you assign here, right, running workout versus exercise, by doing it this way, this dictates which title you use. Meaning, even though I'm saying that workout, the instance workout is equal to 10K run, first and foremost, it has to conform to the exercise protocol. And so to me, it makes sense that the two titles would be different. Why? Because if we look at running workout, again, it has its own title property. And so another thing that we learned is, by doing it this way, the compiler will check to see if there's a default implementation. And then it will check to see if any of the types have the same property within it, which in this case it does, right? So this is a type itself and it conforms to exercise. So first the compiler checks exercise and it sees via the extension that there is in fact a title property, right? So it sees that. But then it checks the actual type running workout and then it sees this. inside the type itself. And so in a hierarchical fashion, it says, okay, if it's in the type itself, this will supersede whatever the default implementation is. So when I said I like letting the type dictate which one I'm going to get, that's what I meant. So by saying that I adhere, or I want to copy 10K run into workout, which is what I'm saying here, but I'm saying that it should conform to exercise first and foremost, because I could do this. You could do that. And then I get the title from running workout as well. That would be another way of getting the values to be the same. But you may not always want that. And so to me, this just makes good sense that, I already forgot what the hell exercise. Yeah, but to me, this makes good sense because you can clearly understand by understanding the hierarchy and how it cascades. You can clearly understand why this would have the default implementation from exercise protocol versus why this one would have the title from its actual type within the body itself. Or sorry, title, not type. Actual title. So anyway, take that for what you will. I like doing it this way. And just to be clear, this way I'm saying is, in this case, extending where I'm pointing to it, like you can see where I'm pointing at. In this case, this way means extending exercise to have a default implementation of a given property you might need, and then just using the behavior of the hierarchy system to override or supersede that within a given type if you need something specific. That way, no matter what, when you're creating instances like this, again, the type that you give it can drive which version of that same property title that you get. Yeah, okay, I think I said that right. Okay, so then after that, I think the other thing that is worth noting, I kind of started in on this and I got derailed, but is this self type, capital S, all right? So we've seen dot self before. And now anything, dot self is a method available on many types. Capital S self is similar, but it's only used in protocols and protocol extensions. And so in this case, like when we extend exercise, if we need a way of telling the method that the return type should be the same as, because in this case we want to be able to accept multiple types into a single method that we define, and this is a way that you can do that. So you tell it using this special self type available for protocols and protocol extensions that you want to return the same type that we give it. So in this case, double would be passed in to our single parameter calories. And so this is just saying, if I pass in a double, I need to get a double back, effectively. And so here we have to call self.self because, self being the type in this case, dot self across the board, not just in protocol extensions, refers to the actual instance object. So when we actually use this somewhere, we need the dot self to refer to the actual instance and to bring that back. But yeah, that's probably easier shown in examples, and we're gonna have a lot of it anyway. So if it doesn't make sense and I didn't explain it great, but we'll see it plenty. So just we'll consider that a brief refresher. But we talked all through this, and matter of fact, maybe I will. Oh, you know what would be better actually? If I just because naturally the Oracle gave us this this great, thoughtful, insightful answer, and we can just go back there and read it. So yeah, self.self. And this probably, yeah, this is, where's the part where they define it? Yeah, up here. So the question effectively was, what's the difference between self and why are we calling self.self, and what is capital S self versus, little self, and all that. So big self, capital S self, refers to the type of the instance that conforms to the protocol within the context of a protocol extension or a type method, which is what we just talked about. So we'll see this only in protocols and protocol extensions. And this is really the big one, because this is true. It's mainly used in type constraints, because that's what it's used for. In the example we looked at, we're using it as the return type. So that's self, capital S self, and then dot self is necessary to distinguish between the type itself and the meta type instance of the type. So that just means that, like here it's showing you the same example we just looked at, where the big self, capital S self, I should call it big self, capital S self, the type self is used as the return type, right? So you couldn't do little self here. So that's its application. But on the caller, so we do var type, it's of type self. Wait, you can do that? Self? Yeah, okay. Well, self.type. Wait, you can do that? We'll try that, but let's find a better, or I guess that makes sense. Okay, yeah, so self.self, when you add .self, it retrieves the meta type of the type, which is a little confusing, but I'm going to ask it the question in a second. But you would think it'd be the other way around, that it would return the type of the object, not the meta type. But I don't know what meta type is necessarily, at least not in this context. But this is particularly useful when you need to reference the type as a value. And that's really the main thing, because that's what we're doing. It's particularly useful when you need to reference the type as a value and then do something with it. So reflection, comparisons, debugging, in our case, comparisons and debugging, it'd be a lot of that. Okay, so example in your code. So when we extended exercise, we added description because we also had to conform to the custom string convertible. So that's why this description property is the description property title itself. Okay, so it's of type string and it should return exercise and then escape, and then this would say self.self, meaning the return type, and then .self would access the value itself, the return value, which in this case would be the string. So we just want to get access to this string that we're supposed to get back. So self.self. It's a little wonky, but like I said, I think the more we write it and see, just see it working, it'll probably make more sense. But just know that the little self, you'll see that often with many types. Capital S self, protocols, protocol extensions. Yep. Yeah, it's good enough. I asked it more things about it, just analogies, but that's not terribly important since we already did that. Okay. So that was the let me see, looking at the code. That was really the crux of what we got through yesterday. Now we did see this thing and we haven't started on error handling, so I assume that's why this is like a precursor, but this is new. Well, specifically the hashtag. And I am intrigued. Looks neat, but we didn't talk about it. So we're going to pick it up right here with error handling right after a bathroom break, brother. That's right. But don't worry, once again, bowels are good. I did not make ultra poor eating decisions last night, but I just get a hankering for many things late at night. And sometimes I regret it in the morning. That's all. Okay, so BRB at, let's see, what time is it? 11:48 a.m. Central Standard Time on Saturday, May 25th, 2027. No, I'm just kidding. So let's come back. How much time do I need? Stretch my legs. Watch a YouTube video. Hate on it a little bit. Okay, let's say 12 minutes. Okay, yeah, 12 minutes. So we'll be back here at noon. At noon CST, brother. Okay, be right back. Go get some water. Okay, false alarm, brother. So I'm back very early. For those that took off to the well, sorry. Sometimes life be like that, brother. You'll be okay. Okay, so now let's time to bounce that ass. Okay, so now that we've done all that jazz, all that review, we can get rolling. All right, so hold on, some bitch. Maybe I'll go buy a chair today. That might be a good idea. Okay, error handling. Oh shit, I'm actually excited for this. As you may have heard, and as I've alluded to, I wrote Go in the past, and there's a lot of you hear a lot about Go's error handling. More than likely, if you've ever watched anything about it, you probably heard that it's dookie trash. You know, I wouldn't call it dookie trash, but it's a bit. It ain't great, but then again, I say that, I mean, it's the only error handling I've ever worked with. So there's that too. But we will go look in, like after we do some error handling here, we'll go and compare it to Go, just as a thought experiment, so you can see. But honestly, I think for me at least, I know that for the most part with Go, this is just a quick aside, but you really don't have to deal with the error handling a whole hell of a lot unless you're writing like microservice apps, anything that's going over the wire, you know, that you don't control, like ingesting data. So for me, I had to deal with it more than somebody would if they were just writing like a, you know, some GUI app or whatever. I don't know, for whatever it's worth. But I'm just saying, it's not like it's everywhere in the code. It's just certain portions, depending on what you're doing, you might have to write, some additional error handling. Okay, but whatever. We're here to learn Swift. Who cares about Go? Okay, so error handling. How often has a piece of software you have been using crashed or done something it was not supposed to? Pretty often. The majority of the time, These issues are caused by incorrect error handling. Error handling is one of the unsung heroes of software development. Nobody thinks of it as a priority, and if it is done correctly, nobody notices. But it is absolutely critical. Users of your software will certainly notice and complain if it is done poorly. Indeed. Yeah, in a past life, we had an on-prem, old-school, application we had written in-house in Visual Fox Pro, if you can imagine, brother. And I would write a lot of the SQL for it, so I worked with the developers a lot, and that was easily one of the biggest issues, was just completely on the Fox Pro side. I mean, like if the app itself would crash, giving no indication as to what the problem was would just really piss people off, and I don't blame them. So yeah, let's get to it. We do got to do this and do it well. Do it well. Classes of errors. There are two broad categories of errors that can occur: recoverable errors and non-recoverable errors. Recoverable errors are typically events you must be ready for and handle. Common examples of recoverable errors are trying to open a file that does not exist, trying to communicate with a server that is down. Okay, yeah, it's a common one. Trying to communicate when a device does not have an internet connection. Okay. I'm not tired. Swift provides you with a rich set of tools for dealing with recoverable errors. You have become accustomed to Swift enforcing safety rules at compile time, and handling errors is no different. When you call a function that might fail with a recoverable error, Swift will require you to acknowledge and deal with that possibility. Non-recoverable errors are just a special kind of bug. Okay? You have already encountered one: force unwrapping an optional that contains nil. How did we do that? Oh, that was like var booty app equals, or not equals, is of type, and then you can do like string with the exclamation point, right? Yeah. String. Oh, well, that's valid. Yeah, so that's the that will force it to unwrap, force unwrap, yeah. Versus doing it like this, where you then have to do the optional chaining, which I think is nice syntax. So we won't be writing any implicit ones anyway, but that's what they're talking about. Where were we? Non-recoverable. Oh, non-recoverable errors are just a special kind of bug. You've already encountered one: force unwrapping an optional that contains nil. Another example is trying to access an element past the end of an array. These non-recoverable errors will cause your program to trap. Pardon me. Thank you kindly. A trap is a command to the OS to immediately stop the currently executing program. If you are running the program from Xcode, it will stop in the debugger and show you where the error occurred. For a user running your program, a trap looks the same as a crash. The program immediately shuts down. Okay. Why is Swift so heavy-handed with this class of error? The name gives a hint. These errors are not recoverable, meaning there is nothing your program could do to fix the problem. Okay. Think about unwrapping an optional, for example. When you force unwrap an optional, Swift quickly checks whether it has a value before trying to access that value. If the optional is nil, Swift will trap. If it did not, the application might crash anyway, or it might try to continue with invalid or possibly corrupt data. What? Think about unwrapping an optional, for example. When you force unwrap an optional, Swift quietly checks whether it has a value before trying to access that value. If the optional is nil, Swift will trap. If it did not, the application... Why is it saying that? If it did not. Oh, if it did not have a value. No, okay, no, that doesn't make sense to me. When you force unwrap an optional, Swift quietly checks whether it has a value before trying to access that value. If the optional is nil, Swift will trap. If it did not, I don't know why that's so weird to me. The application might crash anyway, or it might try to continue with invalid or possibly corrupt data. Yeah, okay, yeah. In this chapter, you will build a very simple two-phase compiler. Oh, Jesus. In doing so, you will implement a function that can evaluate basic mathematical expressions. Oh, sick, okay. For example, if you provide the input string 10 plus 3 plus 5, the function will return the integer 18. Along the way, you will use Swift's facilities for dealing with both recoverable and non-recoverable errors. Lexing an input string. Ooh. Okay, yeah. Let me sit up. Oh, shit. I didn't realize I'd become a systems programmer today, brother. All right, hold on. Okay. The first phase of your expression evaluating compiler is lexing. In computer science, lexing is the process of turning some input into a sequence of tokens. A sequence of tokens. Okay. It's a token is something with meaning, like a number or a plus sign. The two tokens your compiler will recognize, like a number or a plus sign. Okay. Lexing is sometimes referred to as tokenizing. Yeah, that's how I often hear it referred to, because you are turning some input that is meaningless to the compiler, like a string, into a sequence of meaningful tokens. Okay. So save that little nugget. Create a new macOS playground named error handling. Nice. Yeah. Macro, yep. That's the one. Error handling. Okay. I'm gonna show you how to get on. Close this bad boy right there. Good old macOS window management. Hell yeah, brother. And then I gotta drag this little BI over. Okay. Now what do you want me to do? KDD, delete line, I insert. Okay. Enum token. This we've seen before. Enum being one of the two value types, enum and struct. Case number, int. Wonder what that's doing. What is that doing? Okay, never mind. I'm sure it'll tell us. Okay. Case. I didn't know if that was a keyword or what. Okay, case plus. It doesn't look like it. When building something like Alexa, logging your progress can help with debugging later. You will start by logging tokens as your Alexa encounters them. You can define excuse me. You can define how the tokens are printed by adding the custom string convertible protocol to your token type. Update your token enum to conform to it. Okay, so conformance, that was another thing we learned yesterday, or a thing we solidified, is that protocols really are just like classes. You're using inheritance just to a lesser degree. Well, even that's not true. It's just straight up inheritance. It is. Just not as messy as classes. Whatever, doesn't really matter. But it is inheritance. That was the main thing. I wasn't sure how to refer to it, but that is what is happening. Same as with classes and subclasses. Okay, so at least with what we've seen, that is true. All right, so now we need a property named description, because we want to conform to this custom string convertible, and that is the requirement, to have a property named description, and it needs to be of type string. We got a switch conditional statement, so switch self. So little self, again, referring to the instance, not the type. So self-referential to the instance on the caller. So whatever uses this will be able to refer to itself and then do something. So case number, and I assume we get dot number because of here, so we can access it. So case number let in, so yeah, I don't know what that's saying. Return number. Oh, that's a check. Is that what? Maybe. Okay. Enter number. Yeah, it has to be a bool. So it's saying if it is a number, create that temporary constant in and put the value in there, and then return this string number with the actual number that's inside of in, return that string. Okay. No comma. And then our next case statement is plus, so that's our other value in that enum over yonder, brother. And then return symbol plus. Okay. Next, start building your lexer. To lex an input string, you will need to access the individual characters in the input string one by one. You will need to keep track of your current position in string as well. You will need to keep track of your current position in string. Create the lexer class and give it two properties to track these pieces of information. Oh my god. I'm not tired. Okay, enum token var. Where do you want this, brother? Okay, outside, totally new class lexer. Let, so a constant variable named input of type string will be the first property. A mutable variable called position of type string index. I don't think we've seen that yet, using that dot notation on the type. Huh. Is that like a subtype? I guess we'll find out. Okay, so now we have a custom initializer that we want to write for the class Lexer. So input. So we'll have to pass, that's the parameter name input. It needs to be of type string that we'll pass in. So single argument to use that function. And since it's not anonymous, like this, we'll have to give it the parameter name explicitly when we call the initializer. And then self, little self dot input. So this is just saying self.input should equal the string that we pass to it. And self.position should equal input dot start index. Okay. So input is equal to the string that we pass in, and then we make the position start at the beginning of the indexed string. Makes sense. Okay, so then recall from chapter 7 that strings are collections of characters. Yeah. Strings have start index and end index properties that let you step through the characters. Okay, so that's just a, what is that, a method? Has to be. It's not, it's a variable. The position of the first character. I just want to ask very quickly, because it doesn't look like they're gonna address it directly. In the code below, in the Swift code below, please explain what the type index is intended and how it differs from the string type. Okay, string represents the entire sequence of characters as a single unit. When you declare a variable type string, it holds the whole text, not just a position within the text. String.index represents a specific position within a string. When you declare a variable of type string.index, it points to a specific character's location. Okay. Allowing for operations like s. Yeah. Okay. Okay. I guess we just hadn't seen that yet, but that's in the provided input string. This property holds the entire input string that the Lexer will process. Oh yeah, we just talked through that. Yeah. Input string. But let's see. By using string.index, the Lexer can accurately and efficiently navigate through the input string, even if it contains complex characters. Simply using string for the position variable wouldn't make sense because the string represents the whole sequence of characters. Okay. So only other question then is string index considered a type? A nested type, okay, within the string type. But it is not a sub type in the traditional object-oriented programming sense. Nested type. String index is a nested type within the string type. This means it is defined within the string type, which helps in organizing related types together. Okay, not a subtype. String index is not a subtype because it does not inherit from string or any other type in a hierarchy. It stands on its own as a distinct type specifically for indexing into a string. I see. Okay. That's cool. I know we covered this, so clearly I just forgot. So let me save that because that's good to know. And makes a lot of sense. Okay, so. Types and nested types in Y. Okay. All right. Where were we? Here you, okay. Recall from chapter 7 that strings are collections of characters. Strings have, well, wait, I'm going to read this again because now that I know what it is. Okay, so we're saying input's a string, the position is a string index. And in the initializer, we give it the string from here. And then in the self.input bucket, we pass in the string, the entire string that we passed in as the parameter. And then in this bucket self position, we make it the starting index of the string. Okay, yeah, okay. That makes sense. Okay, so then recall from chapter 7 that strings are collections of characters. Strings have start index and end index properties that let you step through the characters. Here you initialize the input property with the passed in string and initialize the position property to the string start index. Lexing the input characters is a straightforward process. The steps you will implement are outlined in figure 23.1. All right. Let's take a better look. We will create. I can finally use my, yeah, brother. Oh, maybe make it a little bigger. Oh, shit. Come on, dude. I think they definitely need to work on their Mac OS implementation. It's pretty buggy, brother. Okay, so this is one. Create an empty array of type token. So an array of tokens. And then it'll get inspected. And then any of these really. So that could be 3. Okay, so we inspect it and then it'll either be a digit, an addition sign, a space, some other character, or there's no characters left. Okay. If it's a digit, then we get the rest of the digits for this number. Get the rest of the digit. Oh, okay. So if it starts with a number, go ahead and bring the rest of them in. Then append the number to the array. Okay. And then get the next character. Oh, and then what? Oh, and then inspect the next one. And then it repeats, okay. Or if it's a plus sign, we just append the symbol to the array. This is pointless. Okay. I mean, not the diagram, but putting the numbers on it is not helping a brother. Gotta find some use for this thing. I'm just kind of pissed at how shiesty it is on Mac. Whatever, go figure. Anyway, if it's a space character, move to the next character. If it's any other character, besides a digit, addition sign, or a space, then just throw an error. And then there could also just be no characters left. If that's the case, return accumulated token array that we've been feeding. Okay. Everything makes sense on a fucking whiteboard. Okay, so you begin by creating an empty array to hold tokens. Where? I assume we're... Okay. You begin by creating an empty array to hold tokens. You then inspect the first character. If it is a digit, you continue to scan forward through the input string, collecting all the subsequent digits into a single number, then appending a dot number to the token array. To the token array. If the character is a space, you ignore it. In all three of those cases, you then move on to the next character in the input string, repeating the same decision-making process. At any point, as you are scanning through the input string, encountering a character that does not fall into one of the three cases above is considered an error. Okay? The input is invalid. Oh, that's the error. Okay. When you reach the end of the input string, the lexing phase is finished. To implement this algorithm, Lexer will need two basic operations. A way to peek at the next character from the input and a way to advance the current position. A way to peek at the next character and a way to advance the current position. Peeking at the next character requires a way to indicate that the Lexer has reached... I need to get a new neck installed. So make it return an optional. Peeking at the next character requires a way to indicate that the Lexer has reached the end of its input, so make it return an optional. Okay. So inside the class, and after our initializer, we need a method. So now we're going to create this method, which is a function. The method is a function associated with the type, in this case, Lexer. Func peek. Empty tuple, because we got no params. Just going, just butt naked. Return type, so this is arrow syntax to indicate the return type, and here we're saying that this method should return an optional character. So either have an optional, either have a valid character value, or it could be nil. Then we open up the function body, bust it wide open, and then a guard clause. So I believe the guard clause was a way to exit the function if, so it would just break out rather, if the condition isn't true. So guard position, we're getting this position value from our property inside this type. So we want to guard against this condition. So if the position is less than the input dot end index, which makes sense. So if that would mean that we're still not done parsing the whole string, or lexing it rather. Yeah, so if it's less than. In the other condition, with our else here, so otherwise return nil. Oh, I see, because it would have to have at least Oh, okay. Yeah, so that's just guarding against nil, because if it was nil, then the position would be nil. And so nil being less than the index of nil, well, I mean, both would be nil. So we know that's false. So that, okay, so that would not work, and it would just exit and return nil. But if the position is less than the end index, meaning position being the start index, so if I pass it, you know, the word symbol, S would be position 0, Y would be 1, M2, B3, right? So in the position value, when it's first initialized, this would be 0. And so when you call the method, 0 would be less than 0, 1, 2, 3, 4, 5. 0 would be less than 5, so that would evaluate to true. Yeah, okay, that makes sense to me. So that would evaluate to true, and if it does, then we want to return input position. What is that saying? Oh, okay. Return the position in the string, but that's an array. I don't know what that's saying. That's an array, but I guess we'll find out. So Command Shift Enter. Okay, so what is that gonna do? Nothing. Try it again. Okay, nothing's happening. It's not ready. Okay. Use a guard statement to ensure that you have not reached the end of the input, returning nil if you have. Okay, so that's a bit that's a much easier way to say it. Okay, so use a guard statement to ensure that you've not reached the end of the input. So that's what this is doing. Right, because if it was equal to or greater than the end of the index, so the end of the word, then you're not done processing. Okay. Yeah. All right. If there is input remaining, you return the character at the current position. Oh, so that's what that's saying. Okay. Okay, so I just have to remember that. It's throwing me off, but so that's how you would say that. Return the position. The string's position. Okay, I guess that does kind of make sense because input is the string. Position is the string's index. Okay. Now that the lexer can peek at the current character, it also needs a way to advance to the next character. Advancing is very simple. Position is an index from the input collection. Advancing is very simple. Position is an index from the input collection. Yeah. And every collection knows how to compute new indices relative to old ones. Get the index after the current value of position using inputs index after method. Oh, nice, brother. And assign that back into position. Okay. So another method here, advance. Empty tuple, so no parameters. It will just return position and it'll be equal to input.index after the current position. So take the current position, give me the next one, return that as position. All right, really. Oops. Before moving on, there is an opportunity here to introduce a check for a non-recoverable error. As you implement the rest of, yeah, it never told us about that hashtag warning thing. It just kind of threw it in there. Before moving on, there's an opportunity here to introduce a check for a non-recoverable error. As you implement the rest of Lexer, you will be calling peak and advance. Yeah. Peak can be called anytime, but advance should only be called if you are not already at the end of the input. Add an assertion to advance that checks for this condition. Oh, Swift has assert. Cool. Add an assert. Okay. So in the advance method, func advance, right above position. Gotcha, brother. Assert position less than the end of the string Okay, so I guess that's a assert checks. You put your condition that should be true in the first argument, and then in the second, whatever you want to return if it's false. Cannot advance past end index. Yeah, like the app that I was referring to, I mean, they would get errors like this and it would piss them off because to a user, I mean, that doesn't mean a goddamn thing, you know, so can't let those bleed out. All right, position. Okay, that's all I needed. The assert function's first argument is a condition to check. If the condition evaluates to true, nothing happens. But if the condition evaluates to false, your program will trap in the debugger with the message you provided as a second argument. Pardon me. Thank you. Calls to assert will only be evaluated if your program is built in debug mode. Oh, that's good to know. Let's just highlight this whole example. Calls to assert will only be evaluated if your program is built in debug mode. Debug mode is the default when you're working in a playground or running a project in Xcode. Release mode is what Xcode uses when you build an app for submission to the App Store. Okay. Among other... Oh my gosh. Sheesh. Among other things, building in release mode turns on a number of compiler optimizations and removes all calls to assert. Okay. If you want to keep your assertions around even in release mode, you can use precondition instead. It takes the same arguments and has the same effect as assert, but it is not removed when your app is built for release. Oh, so if you want... I'll have to ask about that. Both assert and precondition are used to trap if a condition is not met. But if you need to unconditionally halt program execution, You can do so with fatal error, which accepts a string argument that will be printed to the console just before trapping. A string argument that will be printed to the console. That's really cool, but I just have so many questions. Okay, we did see that precondition earlier. Yeah, my mind's racing. Okay, why did you use assert instead of guard or some other error handling mechanism? Assert and its partner precondition are tools to help you catch non-recoverable errors. As you're implementing your lexing algorithm, you're advancing an index from the beginning of the input to the end. You should never attempt to advance past the input's end index. Okay. Adding this assertion will help you catch any mistake you make that introduces a bug of this kind, because the assertion will cause the debugger to stop execution at this point. Because the assertion will cause the debugger to stop executing at the point, helping you identify the error. The alternatives to this assertion are to not advance the lexer's position or send an error back to the user of your lexer, neither of which makes sense. Now that the lexer class has the building blocks you need, it is time to start implementing the lexing algorithm. The output of lexing will be an array of tokens, but it is also possible for lexing to fail. To indicate that a function or method might emit an error, add the keyword throws after the parentheses containing the arguments. This implementation of lex is incomplete and will not compile, but you will finish it shortly. Okay, so before we do that, I want to ask the Oracle about this precondition here. Doesn't have to be a long drawn out thing, but I need to know example use case in Swift when considering the use of assert versus precondition. Please give examples of one use over the other and why. Pardon me, my gosh. I don't feel sleepy. You know what though? It's a great excuse to order some goddamn coffee, brother. That's probably what I need. Starbucks. Shoot, what was I thinking? All right, let's see. Don't worry, babe. We'll get you some when you get here. She gets upset when she shows up, sees a Starbucks bag. Oh man. View. There. Thank you, brother. Word to your mother. Tip. I don't know about that, brother. No, I'm playing. In my opinion, the Uber Eats drivers, the good ones, I mean, they're doing God's work, so definitely tip those brothers. But the other, you know what's bullshit? Just quick aside. Like, I'm totally for tipping servers and anyone actually doing a service, you know. But I went to a Ben & Jerry's the other day. Me and my girlfriend went. And, you know, I mean, those are just, it's a cashier. And they put your ice cream in there, you know, but they're not getting paid like servers. They're getting paid, you know, minimum wage or whatever. I don't know what they're getting paid, but it's none of my business. But my point is, why are you asking for tips when I'm checking out at the counter at a Ben & Jerry's, bro? What? Huh? Get out of here. Or at a coffee shop even, like where you just walk in, you order at the counter. They set it on the counter when it's ready. You know, they call your name out. You get up, go get it. I don't know, man. You know, Anyway, I digress. Before I get canceled up here. So precondition, so assert is for debugging. I get that, they said that, but I was hoping to get, let's see, precondition. Okay, here we go. When you use assert, when you want to catch programming errors during development, but do not want these checks to impact performance or behavior. Okay, so that's good. Yeah, that's exactly what I needed to hear. Precondition, the purpose. Precondition is used to enforce conditions that must be true both in debug and release builds. It causes a runtime crash if the condition is false. Regardless of the build config, behavior in both debug and release, if the condition is false, the program will crash. Yeah, okay. I mean, I don't see why you would not, unless they're telling me there's like a big performance hit or something. Like, I don't see why you wouldn't use preconditions. Consider a scenario where you have a critical function that must have valid input to ensure the stability of your program. For example, a function that calculates the square root of a number. Func calculates square root, takes a double as an input, returns a double. The precondition is that the number passed in must be greater than or equal to 0, enforcing that it is a non-negative. Okay. Return squirt number. Yeah. When I couldn't help myself. Assert used during development to catch programming errors, ignored in release builds. Oh, we read that. Okay. Choosing between them depends on the criticality of the condition you're enforcing. Is there a performance penalty for using precondition? It does introduce a small performance penalty. A small one. Yeah, come on, brother. Nah, I mean, I would start with it. In my own app, I'm just saying I would start with it. And then you can just pull it out if if it's dookie trash, like it makes it really slow. However, for simple conditions, checking if a number is greater than 0, performance impact is minimal. When a precondition fails, the program terminates and generates a detailed error. The termination process itself has some overhead, but this only occurs if the precondition fails. Okay. Inlining and optimization. Swift's compiler is quite sophisticated and can optimize precondition checks effectively. If the compiler can determine that a condition will always be true, it may optimize away the check entirely in release builds. Oh, so it still might pull it out. Okay. However, this isn't guaranteed and depends on the complexity of the condition and the compiler's ability to infer its outcome. That's why I don't like this whole thing of just using the type inference, because you actually do lose, like, I mean, this is proof of that, but you actually do lose potentially, not definitely, but you potentially lose some performance here, basically what it's telling you. Because if there's too much, or if it's like a long chain of inference or whatever and it can't figure it out, then it might not be able to optimize it away for you. But if you just statically type everything, like I think you should, like, man, this is kind of the whole point to me. I don't know. It's just an opinion, but we'll see how true that holds. Okay, example, let's compare the performance impact of a function using precondition versus one without. All right. Process with precondition. One input, it's a number, and it has to be an integer. And then inside the function body, the precondition is that the number must be greater than 0. Oh, okay. I mean, that is pretty, okay, that's easy to understand, yeah. So the first thing it's going to do is check. And then if that's true, or if it's false, it'll crash. If it's true, then it can just do whatever else you need to do. Yeah, okay, yeah. Yeah, without. All right. Measuring, yeah. To quantify the performance penalty, you can use Swift's performance measurement tool like XCT performance measurement. Oh, sick. Okay. In unit test or instruments and Xcode. That is cool, man. Small, you should be weighed against benefits. For non-critical checks or in performance sensitive, you might want to consider. Okay, so then if that's true, can you describe use case where it would be a seemingly no-brainer to use preconditions even in the presence of a performance? Okay, F&O. It's always F&O, finance and ops. Yep. In a banking app, you have a function to process transactions that deducts an amount from one account and credits to another. Yeah. In a banking app, you have a function to process transactions that deducts an amount. Oh, and the GO, yeah. Ensuring that the transaction parameters are valid is crucial because incorrect handlings could lead to financial discrepancies, fraud, or legal issues. So, you know what really pisses me off? Like, actually really pisses me off is, all right, okay, first of all, I know I've said this before that Python is dog shit, and I do believe that for the most part. I'm not saying it's not a useful tool, just overall I give it a score of dog shit. Okay, I'm sorry. But I've used it before, and I will probably continue to use it at some other point in my life. And Python even. I'm calling out Python just in the sense that if you take it from the standpoint of it's dynamically typed, right? It's like the scripting language. It doesn't really get any more simple than Python. I guess you could argue maybe Lua or JavaScript even, but I don't know. It doesn't matter. The point is you don't have to give it types. It's rare, you know? And even that being the case, it still has assert, you know, just like precondition. So there are ways to control it. There's a mechanism there to make sure that whatever it is that you need to happen happens, right? Okay, so that's the worst example, and even that has ways to check your work. Well, the application that we used to use, effectively what I'm saying is this used to happen all the time, or the example that they just gave used to happen all the time with these old apps. And it's just incredible to me that, you know, because my ex company, we were a reseller of an ERP. So we were licensed to resell this ERP package, this accounting package that controlled the GL, like they're saying. That's what they're talking about when they talk about credits and debits. And then we wrote an in-house thing that plugged into that. But we had to deal with this shit all the time because as the reseller, your customers come directly to you to support the product. But the actual source code is controlled by, you know, the vendor. And so there was just constant. I was the product director for a number of years for them, and that was one of my duties, was to report, you know, bugs in the software that we discovered to our vendors because they're the ones that gotta patch it. And it's just crazy to me like even stuff like this. I know they're saying right here, like, yeah, banking, F&O, you gotta guard against these, and you would think it's a fucking given, but no, it's not. We would constantly have to go in there and affect the data directly in SQL, which is bullshit. But yeah, it's wild to me that stuff like this still happens when there's clearly methods all around to check for that stuff. I don't know. It's just it's just all fucked up. You know what I mean? No pride in your product. I don't know what it is. It doesn't have to be perfect, but certain things just come across as, I don't know this for a fact. It comes across as you're not even trying, you know? Because it was a smaller company in terms of the vendor that distributed that product. And, you know, they got to a point where they were sitting pretty. Recurring revenue was paying for everything. You know, they just quit trying. Just quit trying. One of the many reasons I parted ways. But anyway, I digress. Okay, so where were we? We were reading about preconditioned use cases and all that jazz. I think I get the picture, so we can move on. All right, so why did you use assert? I read that part. Not recoverable. Okay, yeah, we read this whole part. So we're going to type this up. Declaring the throwing Lex method. Okay. Func advance. Where's that at? Okay. Right below that. So another method. Func. Lex. No parameters. Throws. Finally, we get here. Throws. Where'd it go? Throws. And the return type is an array of tokens. And in the body, we have a property, tokens, and that will hold the array of tokens. So we're just initializing an empty token array there. And then we have this conditional statement. So while let next character. Okay, next character will equal the output of the peak method. Which is what's giving us our position within the index on line 27, or rather 31 specifically. Okay, so that gets us the position. Character. Oh no, sorry, not the not the 0, 1, 2, 3, but the actual character. Yeah, because the return type is an optional character. Okay, so peak, and then conditional switch statement. Next character. Case. First case is 0. So our first conditional is if the next, or the value in the next character is between 0 and 9, stringified. What is that? Comment start of a number. Need to grab the rest. Oh, right, we saw that in that chart, so that's what we would do. So if it is a digit, grab the rest of that number. So break to do. Replace this with real work. Okay. Heard that before. Case. Oh, I see. So we're just doing the, yeah. Cool. So if it's a plus sign, then return tokens. Return tokens.append. Tokens.append. tokens. Oh, so if it is okay, if it's a plus sign, then append plus, which just itself returns this string. Okay. And then return a plus sign and then advance to the next position. Okay. Case. And then here's our space character. If it's a space, then just advance to ignore spaces. Okay, I see. So in every case, we're doing some kind of advance, and I imagine here we'll have to some code to grab the rest of the string and then advance. So okay, so then it's making sense so far. IMO, and finally default. So since switch statements must be exhaustive, you either have to list cases that cover the full gambit or have a default fallback, like so. So something unexpected. Need to send back an error. And then break. And we gotta come back, do something here. It's formatting the to-do, so I assume it's keeping track of that somewhere, which would be cool. Replace this with real work. All right, so that is the while loop there. And then after that, we want to return tokens, which is our array. So that's our array, and then that's what we want to return. So then that all checks out, brother. All right. Goddamn back. Shit. Coffee is 7 minutes away. You know what's bullshit? You know, they used to, like, it used to be that when you ordered something on Uber Eats, or really like any, I don't know if other apps do this because I don't use other apps, but I would bet they do. Or if they're not yet, they will. But, you know, if back in the day, if you ordered something on Uber Eats, there was really no thought about whether or not the person that's bringing your food is going to make multiple stops. You just, at least in my mind, I'm like, well, my assumption is that if I'm being asked to tip somebody that, you know, similar to a server, it's like, hey, no, they're, I guess that's a bad analogy because it would actually fit. Whatever. I'm trying to make a point here. My point is that we used to it was just assumed that you were going to get the thing that you ordered, whatever food, delivered straight to you. Because, you know, if it's hot food, you want to get it hot. If it's meant to be cold or frozen, you don't want to get it melted. So there's just kind of this presumption, right, that the food is going to show up fresh within enough time. Otherwise, don't sell it on Uber Eats, right? And everything was cool. Now it's like an extra, literally $4 priority to get the same thing now, but they've just put it behind a paywall. So now if you want something delivered directly to you, oh, it's an extra $4. Otherwise, we're going to send your Uber driver on 3 different stops before, you're 4 of 5. So by the time you get your shit, it's, melted or cold, or, you know what I mean? Just some sorry MFs. That's all I'm saying. Just greedy. But, obviously I pay it. I'm just saying. I don't want to wait, but I just order less. You just have to. It's annoying. But yeah. I just want to get that out there. Okay, there are 2 cases left to implement. Wait, did I read this? No, I have not. Okay. You have now implemented most of the lexing algorithm. You start by creating an array, tokens, that will hold every token you lex. Yeah. So here. Use a while let condition to loop until you reach the end of the input. Here. To the end of the input. For each character you look at, you go into one of the 4 cases. Bam, 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 bam. Wait, 1, 2, 3. Yeah. Into the 4 cases. And you have implemented what to do if the character is a plus, append plus 2 tokens, and then advance to the next character. Or a space. Ignore it, advance to the next character. There are 2 cases left to implement. Let's start with the default case. If this case matches, then a character you were not expecting is next. That means you need to throw an error. In Swift, you use the throw keyword to send or throw an error back to the caller. What can you throw? You must throw an instance of a type that conforms to the error protocol. Most of the time, errors you want to throw will lend themselves to being defined as enumerations, and this is no exception. Excuse me. What should you name your error-conforming enumeration? One option would be to name it Lexer error. Lexer error would be acceptable, but it also adds another type just for designating lexing errors, which is not ideal. A separate type would suggest that Lexer error has meaning beyond and outside Lexer. Recall from chapter 16 that you can nest types. You can use a nested lexer.error enumeration that makes it clear that the error cases it provides are directly related to Lexer. Okay. Yeah, it makes sense. Hold on 1 sec. I'm going to turn the error on. Sorry for the introduction of additional noise. You can probably hear a light hum now. There's nothing I can do about that turbine running in the back, so we'll try to drown it out. It shouldn't be on for too long though. 2 minutes away. Come on, coffee. I need it. All right. So, Lexer error. Oh yeah, we're talking about doing a nested type. That'll make more sense. Okay. Declare an enumeration nested inside the Lexer class to express lexing errors inside the Lexer class. Okay. It's a big ass class. How about that? Enum error. So we'll do it at the straight up at the top, brother. You got it. Come on. Enum error. Get there. Case invalid character. What? Is that how you type a case? Maybe that's just syntax I don't remember, but that's now the second time, so let me go ask. What does this mean if this is a case in an enum, is the parentheses how I indicate the type for the invalid character is a case in the enum that has an associated value of type character. Okay, so that is what that means. It's just different looking syntax. This allows invalid character case to carry additional information, the invalid character, along with it. Is there any other scenario where the type is indicated in this way? Used to seeing the okay, so that we will see it elsewhere. In Swift, there are scenarios other than enum associated values where types can be indicated without using the syntax. Here are a few examples. Okay, closure. When defining the parameter and return types of a closure, you use parentheses to indicate the types. Defining parameter and return types, use parentheses to indicate types. Like closure. Oh, but you still have the colon, brother. Come on now. Wait, so it's of type, here's the return type bool, and it's equal to this logic. Okay. Okay. Function types. This is, okay, it's kind of the same though, so still in the signature. This is where I was used to seeing it. So this is saying that the type of that parameter is this closure. So the argument would be a the function itself. Return integer. Ooh, we haven't seen that yet. On. Okay. Let sum, so this would be an instance of that closure, and its type is the okay, so that makes sense too. And then finally, what? Tuples to group multiple values and their types. Let person, and it's equal to this tuple, or not equal to, the type is name string, age int. Okay, so a few different ways. And then enums that we just saw. Okay, fair enough. Just curious. All right. Oh, it's here. Hell yeah, brother. One sec. Trick me. Where is it at? Of course, there's always one guy that can't get here, brother. I order all the time and they get up here. I'm gonna have to go find this joker. I'll be right back. Oh my gosh. Unfucking believable. Alright, just turn the air off so the stupid ass fucking, sorry for all the cursing, fuzzy noise should go away shortly. And, if you're wondering, I did get my coffee, but it was leaking. Bottom of the bag is drenched with some of my damn coffee. How does this, how do you manage to get, doesn't matter. So anyway, I just had to chug a venti with 6 shots in it. So I'm about to be, ooh, you know. So before my limbs start shaking like fucking crackhead, we better get cracking. No pun intended. Okay, so I really need to uninstall the app. It's just crazy, brother. Well, I mean, goddamn. All right, enum error case. Did we do this part? We did. All right, so we got that part. Enum error. And we now understand that this is, in fact, relative to enums, how you can indicate the type that a value should be. Okay. Lexer.error needs to conform to the error protocol. Okay. So then we will do such. Do as such. So now it's conforming. Directive to add this conform will fail, but try it anyway to see the error. Okay, we see the error. All right. You will get a number of error messages in the console. Find this one. Error handling .playground 1810 error. Error has a raw type that depends on itself. Enum error. And there it is. Okay. The compiler is confused because it thinks you're trying to declare an error type using itself. So don't name it error. How can you tell the compiler that you want to use the error protocol from the Swift standard library? Swift does not have explicit namespaces, unlike languages such as C++. Instead, all types and functions are implicitly namespaced to the module they are defined in. I don't like that. Okay. You typically do not need to think about which module you're working in. If you're writing an iOS app, for example, the entire app lives in one module. Really? Okay, I would keep an open mind. So in Go, they use different terms, but they do let you have that control, and I always like that because you have, like in Go, the module is at the app level, but then you have packages. So you have main package, main function, but then you can also have other packages, and then just call on functions that way. It's like package name dot the function or whatever. Hopefully this is it can achieve something like that. Declaring lexer.error is one of the rare cases where being aware of modules is useful. Okay. Types and functions that are part of the Swift standard library live in the Swift module. types of functions live in the Swift module. Oh, I see. Okay. So, oh. Oh, so it is kind of the same thing. They just call it something different. Because that is, I mean, that's the same as if you were to pull it in from Go. Okay. Okay, good. All right, so you can specify that you want the Swift module's error type by its full name, swift.error. Okay. So, swift.error. Okay. Then, oh, whoops, where'd it go? Okay, so now add the module name to fix your declaration. Okay, we did that. Command click on the Swift error protocol and choose jump to definition. Command click on Swift.error protocol. Command, I did. What? Oh, dude, this is perfect. This is what I thought the option click would do, which just calls the documentation, but oh, this is great. Okay. Brother. Why don't you say anything sooner? Command click. Okay, choose jump to definition. Choose it. Protocol and choose jump to definition. Well, it didn't let me pick anything, but it just took me there. So, where is the... Wait, let's do that again because I don't know what. Command click. Or maybe I need to do that on the error word itself. Okay, my fault. All right, public protocol error. Nothing in it other than it conforms to sendable. So you will find that it is an empty protocol. The behaviors that Swift wants from error conforming types are added via protocol extensions in the standard library. This means that any type you write can conform to error just by stating that it does. This means that any type you write can conform to error. What? This means that... Oh, because there are no... It's an empty protocol, so there's nothing to conform to. It just is if you say it is. Okay. Enumerations are by far the most common errors. When something fails, you usually have a discrete list of reasons for the failure, which are representable by enum cases. Okay. Click the back arrow in the Xcode toolbar to return to your playground. Now that you have a throwable type, implement the default case in the lex method to throw an instance of your new error enum. Click the back arrow, this thingy. Oh, okay. Implement the default case in lex method to throw an instance of your new enum error. So our default case, we want to get rid of the break. So here, oops, throw Lexer error. Okay, so Lexer, because that's the type that it's in, we use dot notation to access the error type, the nested type. We just define that conforms to error protocol, and then within that, all right, and then the dot invalid character, because that's, well, I mean, that's the only property. Only property we have in there, right? Where is it? Yeah, it's literally the only one, so that's where that's coming from. Okay. Invalid character. Next character. All right. Back throw it. Okay. And then return token still. All right. Like return, throw causes the function to immediately stop executing and go back to its caller. Finally, the Lexer needs to be able to extract integers from the input. Finally, the Lexer needs to be able to extract integers from the input. Create a get number method that builds up integers one digit at a time using the same peek and advanced tools you are using in Lex. Next, update Lex by adding a call to get number and appending the number to the array of tokens. Hot dog, okay. So here. Func. So another method, get number, no argument or no parameters. Return type will be integer. And then inside we want a mutable property or mutable variable called value with starting value of 0, and then a while conditional, so while let next character equal the output from the peek method, and then looks like we're doing something similar to what we did in the other one. Wait, is this the same? Oh, no, it's different. Okay. Switch next character. Again with the 0 through 9. 9. If it matches, then another digit. Add it into value. Let digit value equal, oh, this is what we're using to get the rest of the number. Okay. Let digit value equal int string. Okay, what do we? 1, 2, what is that? What's that character? Is that a, oh, it's an exclamation point? So we are force unwrapping this thing. I'm not sure what that means in this context. doesn't seem like it's doing the optional thing. But anyway, okay, so we're saying stringify the next character and then convert it to an integer and put that in the digit value constant value equal 10 times the value plus digit value. Okay, so value starts at 0, peak at the next character. If it's between 0 and 9, then let the digit value equal that character as an integer, because we know it's a number, so that should work. And then value, which is 0 to begin with, now we set that equal to 10 times value, which would be, at least in this case, 0 plus whatever that digit was. I wonder why 10 times the value. I'm sure they'll tell us. Okay, so then after that we advance still. All right. So that is case number 1. And then to make it exhaustive, we have a default case. So if it's not a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, this applies instead. So something unexpected, need to send back an error. Okay, and then return value. Okay. So we just return 0. Okay. Default, what else do we do? Then return value. Missing return in a local. Oh, and then return value. So if it okay, I won't try to guess that one. I don't know what it's doing. Okay, then in this other while loop, we need to, oh, now we need to apply it. So down here in the default to do, or no, here, right? 0 through 9, yeah. Okay, so now we can actually implement our new method. Let value equal get number. So that's the method we just wrote. So get number, and then tokens. So append to the token array the number value. Return number value. Let value equal. Okay, at this point all your errors should be gone. Okay, they do be. Yep. Command Shift Y, get out of my way. Get number loops over, wait, let me get there. Where are you at? There you are. So this guy. Get number loops over input characters, accumulating digits into a single integer value. Accumulating digits into a single integer value. Oh, a single integer value. Yep. Okay. Note that you do something we have cautioned against. Force unwrapping and optional. So that is what that is. But why is... Oh, I guess somewhere... Oh, because character is an optional. And we call... Oh, okay. That's why. So peak is dealing with an optional character. Okay. All right, brother. Well, then that's what that is. All right. Note that you do something we have cautioned against: force unwrapping an optional in int string next character. However, it is perfectly safe in this case because you know that next character contains a single digit. Oh, because of our case. Okay. Converting it to an int will always succeed and never return nil. As soon as getNumber encounters a character that is not a digit or the end of the input, it stops and returns the accumulated value. Lexer is complete, and it's time to put it to the test. Write a new function at the bottom. Okay, we're going to do that. We are going to do it, but you can't just... Yeah, no, you can't leave me hanging like that, brother. I just want to... I want to understand why it's... Why is it doing that? Given the below Swift line code, how do I go to the top? Whatever. Given the below Swift line code, please explain why. Where is it? Why we would multiply the in the provided Swift code, the line where we multiply the value by 10 within the getNumber function is crucial for correctly parsing multi-digit numbers from the input string. Let's break down why the multiplication is necessary. Yeah, so if you don't know what I'm talking about that right there. It's from the book, so they just told us to write it. Didn't necessarily explain why, and it's not obvious to me, so here we are. Initialization. The value variable is initialized to 0. Yeah. This variable will store the numeric value as we parse through the digits in the input string. Okay. Iteration through characters. The while let next character equal peak loop. Son of a gun. If only I was more limber. Okay. Ooh, that's way better. Loop iterates through each character in the input string as long as its digit is between 0 and 9, 0 and 9. Character conversion and accumulation. So I get that part, but okay. For each digit character, digit value is computed by converting the character to an integer. Yeah. Oh, wait. I gotta check something real quick. So this is, next character is, oh, that's coming from there, but oh, okay. I think I get it. So if next character is equal to peak, and peak is of type optional character, yeah, okay. That's why we gotta. So it starts as optional character, and then I stringify it, and then I intify it, if that's a word. It is now, brother. All right, so what else? Character conversion. For each digit character, digit value is computed by converting the character to an integer. Yeah. Value equal 10 times the value plus digit value. This line is key for building the multi-digit number. Here's how it works. Initial digit. If the input is 1, 2, 3, when parsing the first digit 1, value is 0. Oh, right, sure. When parsing the first digit 1, value is 0, because that's what we said it should be here. Okay, so value is 0 and digit value is 1. Calculation, 10 times 0 plus 1 results in value equals 1. Okay. Subsequent digits. For the next digit, value is now 1 and digit value is 2, because 2 is the next character. Yeah. Okay. Calculation. Value equals 10 times 1, 10, plus 2. Results in a value 12. For the next digit 3, value is now 12. The digit value is 3. Calculation, value equal 10 times 12. 120 plus 3 results in value. Oh, man. Okay. No, yeah. Man, hot dog. Okay. Well, I mean, it makes sense, but well, yeah, it makes sense. Cool. Okay. So importance of multiplying by 10. The multiplication by 10 is crucial because it shifts the current number to the left by 1 decimal place. I see. Man, these guys, where do they come up with this stuff? Okay, so then in that case, let's move on. At this point, all your errors should be gone. Okay, we did that. Lexer is complete. It's time to put it to the test. Write a new function at the bottom of your playground that takes an input string and tries to lex it. Then call it with a couple of trial inputs. This function will not work quite yet. As you type it in, try to figure out why. Write a new function at the bottom of your playground. Okay. Func evaluate. Evaluate. So we have an anonymous external parameter, so we won't have to write the parameter at all, in other words, but the internal parameter name is input, and it takes a type of string. Function body, bust it wide open. So then we first print evaluating escape character, string interpolation. So first we print evaluating, and then whatever the string of the input is, whatever we pass to it. Then we have a constant variable, let lexer equal type lexer input let lexer equal lexer. So an instance of lexer with, oh, so we want to make it equal to an instance of our lexer with Oh, there. Oh, okay, so that's our initializer. Gotcha. Okay, Lexer dot, I got you. So that's it's the only one, so we don't have to specify in that way, but that's what we're saying. So we want an instance of the Lexer. We have to give it the parameter name because that's how we designed it here. So we don't have it anonymous like that. So that's why we got to do it. And then it's of type string. And so we just want to make that equal to an instance of it in the input. Will be whatever we pass in. Okay, and then let tokens equal Lexer dot lex. So that's the method that we defined in the class Lexer. Where is it getting? Oh, right there. Duh. Okay, Lexer dot lex, but what's this? Call can throw, but it is not marked with try, and the error is not handled. Lexer equal Lexer input. Oh, okay. So we get access to Lex because Lexer is an instance of it. Okay. Call can throw, but not marked with try. What does that mean? So if we go look at Lex, throws. Oh. Okay. But we're still not done writing it, so let's go back to that. Let Lexer equal Lexer.lex. And then finally print. Oops. Lexer output. Escape character tokens. So then we just print the array of tokens. Lexer output. Yeah, okay. And then evaluate. Plus 3 plus 5. Evaluate. 1 plus 2 plus 3. U. Okay, this function will not work quite yet. As you type it in, try to figure out why. I'm gonna go out on a limb and say this is why, but it's because it's not marked with try and the error is not handled. Just a wild guess. Okay, so evaluate takes an input string, creates a Lexer, and lexes the input into tokens. Yep. But the compiler does not allow you. Nope. But the compiler does not allow what you have entered. Note the error message on the line where you call Lex. Call can throw, but it's not marked with try. Yep. The compiler is telling you that because the Lex method is marked as throws, calls to Lex must be prepared to handle an error. Okay. Catching errors. To handle errors, Swift uses a control construct that you have not yet seen. Do catch. Do catch. Swift uses a control construct here. Okay. Do catch with at least one try statement inside the do. Do you, boo-boo? Okay, we will explain in a moment. First, modify evaluate to use this control flow to handle errors coming from Lex. Okay, brother, relax. So then let tokens. So break that baby up and then do. Let print catch print. An error occurred. Escape character string interpolation error. And then close that out. Okay. What do these new keywords mean? Do introduces a new scope. Control I. Okay. I thought that formatted things, but apparently not. Or maybe is that what it's supposed to look like? I guess so. Okay, what do these new keywords mean? Do introduces a new scope. Much like an if statement, inside the do scope, you can write code as normal, like calling print. In addition, you can call functions or methods that are marked as throws. Oh, you can write code as normal and call functions or methods that are marked as throws. Okay. Each such call must be indicated with the try keyword. After the do block, you write a catch block. If any of the try calls inside the do block throw an error, wait, so you're saying, okay, Lex, if we go to the definition, where the hell? Okay, so I can call it because I've marked it with throws. But now I get an error. Cool. Man, I like that. Okay. What do these new keywords mean? After the do block, you write a catch block. If any of the try calls inside the do block throw an error, the catch block will run. If any of the try calls inside the do block, oh, well, just this one, because that's the one marked with try. The catch block will run. Okay, so if it throws, then this runs. Ugh, okay. With the thrown error value bound to the constant error. Where is that at, though? Where do we... Where is error? I guess that's another implicit thing. It's like always there. Maybe, I don't know. We didn't, right? Error. Error. Yeah, we don't have, okay, so that must be some implicit thing. With thrown error value bound to the constant error. You should now be seeing the output of running evaluate in the debug area. Okay, let's run it. Call can throw but not marked with try. Oh, I didn't finish my, okay, my bad. First modify evaluate coming from, okay, do let tokens equal try. Oh, okay, try lexer.lex catch. Okay, that was it. So now run it. Okay. You should now be seeing the output of running evaluate in the debug area. Oh, in the console. Get up here, brother. And there we go. That might be hard to see. The catch block you wrote above did not specify a particular kind of error. So it will catch any thrown error. Okay. You add catch blocks to catch specific kinds of errors. In this case, you know that the lexer could throw a lexer.error.invalid character error. So add a catch block for it. Wait, so what did it say? Evaluating 1 plus 2 plus 3, an error occurred, invalid character T. Oh, cool. Okay, I see. All right, so back to a regular human size. Add a catch block for it. So in our do, let, oh, okay, catch lexer. Oh, I see. So if I just have the single, it'll catch all errors, but I can specify if I want specific output for a specific error. Error.invalid invalid character. Let character. Okay. And then print input contained an invalid character. And input contained an invalid character, and then whatever that character is. Okay. You add a catch block that is specifically looking for the lexer.error.invalid character error. Catch blocks support pattern matching just like switch statements, so you can bind the invalid character to a constant for use within the catch block. You should see a more specific error message now. Congrats, the lexing phase of your compiler is complete. Before moving on to parsing, delete the call to evaluate that is causing an error. Oh. Wait, what? What did I not do? Catch lexer.error invalid character. Let character. Open scope. Print input contained an invalid character. Character. Scope. What's the problem, brother? Errors thrown from here are not handled because the enclosing catch is not exhaustive. Oh. The enclosing catch. What do they have? Let, lexer, and the same thing. Do. Just like switch statements, you can bind invalid character to a constant for use within the catch block. Input contained. Well, that's what we had before, but what did we change that made it? Before moving on to parsing, delete the call to evaluate that is causing an error. Here's stuff from here not handled. I must have missed something here. The catch block you wrote above did not specify a particular kind of error, so it will catch any thrown error. Oh, it was gone whenever I had just this, right? Oh, but then that's not in scope. Well, what's the deal, brother? do let tokens equal try lexer.lex. Get number. What's the problem, bro? Errors thrown from here are not handled. Not exhaustive. Killing me, man. Catch lexer.error. Let character. You add a catch block that is specifically looking for the lexer error invalid character error. Catch blocks support pattern matching just like switch statements, so you can bind the invalid character to a constant for use within the catch block. You should see a more specific error message now. I mean, I didn't really though. Do I get anything here? Come on, man. Never know, so maybe I'll break the cardinal rule and do the old copy paste just to see if it's errata or not. Wait, what, dude? Character. Do let print. What did I have that's different? Oh, I can do this. Yeah. Func evaluate input string. Input. Lexer is equal to lexer input. Input do. What the fuck? Okay, print lexer output tokens. That's the same. Then our catch block. Lexer error invalid character. Let character. Invalid character. Print. Input contain invalid character. Invalid character. Oh, duh, I'm missing a whole ass catch block. Oh, I missed it. I just saw the bold, but tricky. But that wasn't, it was. Damn, okay, it is my fault. Womp womp. Okay, well, at least my shame is public and documented. Okay, so then now where are we? That is causing the error, so get rid of this. Okay, so now we're caught up. Parsing the token array. Is that really what time it is? Okay, yeah, it is. Now that your lexer is complete, you can turn an input string into an array of tokens, each of which is either a number or a plus. The next step is to write a parser whose job is to evaluate a series of tokens delivered to it from the lexer. Yeah, we're bumping up on 3 hours. I think I will wrap it up here, folks, because we just finished a little section there. So, as per usual, thank you all for hopping in, hanging out today. And as always, if you would like to check me out elsewhere, I also have a stream that comes on at 9 p.m. Central Standard Time each day. And I am on day 62 of 100 Days of Ranked Halo Infinite. So make sure you come back and check that out. My gamer tag is on the screen. Actually, I need to update these. This is horrible. Just watch me on X. How about that? Because it's on the same. That's the easiest way. But yeah, you guys, thanks for hanging out. We'll be back tomorrow, 11 a.m. Central Standard Time for the Swift Learn Along. It'll be episode 36. Otherwise, I'll see you tonight on the Halo stream. Good day to you.